Hello, welcome back to the second part of this video, which is calculating heat load. So again, I'm starting here off on our Blackboard page, where you will see here you have calculating heat load as the third item down. So basically click on that. Again, I have it open here in the Excel document already, and we will bring up our paint file as well. So in this diagram you can see I have drawn a very fundamental house. So we've got the dimensions of the house, 3 meters by 4 meters, so that's the floor plan, and we have a height for the floor to ceiling of 2.5 meters. I've got a door and I've got 2 windows. So basically that's really all the information that you need for this exercise. So in the first case here, you'll see you've got a floor area. So 3 by 4 is the floor area, so it's 12 meters squared. The story height is 2.5 meters in height. So all you have to do really is just go down through this Excel document and infill all of the yellow spaces. The green spaces are there, and if you notice, whenever you click on a green space, you will always come up with a formula. So the green space will always have some kind of formula in it, so you don't click or you don't enter anything into green space, just into yellow space. I've noticed here actually that should be a green space, this one. But so the first thing we need is the overall dimensions of our building, which is the area, which is 12 meters squared, and the height is 2.5 meters. So that gives us a cubic volume of space within the building of 30 meters cubed. It also gives us a floor area of 12 meters squared. Then we look at the heat loss through the fabric of the building. So first thing we're going to do is work out the roof area. The roof area is exactly the same as the floor area, so these here should be the same. Sometimes they're different because maybe you've got a larger say ground floor, maybe you've got a garage on there with a separate roof or whatever, but generally the roof area is the same as the ground floor area, so we'll enter that as at 12. Then we go then to our walls. So the wall area is the total wall area of the building. So here we have 2.5, so I'll change the size of this. So we have 2.5 I should really I'll use this here, so rub that out. That's that, and then I will use that. So we have 2.5 multiplied by 3 multiplied by 2 equals, because we have this wall here and we have the similar wall over here. Then we have 2.5 multiplied by 4 multiplied by 2, because we have this wall here and this wall over here. So 2.5 multiplied by 3 is 4, 5, 7.5. 7.5 multiplied by 2 is 14. Okay, so that there is 14 meters squared. Then we have 2.5 multiplied by 4, so 2.5 is 5, 10 is 20, so we have 20 meters squared there. So that means our total wall area, excluding windows and doors, is 34 meters squared. The only thing is we have a couple of windows to consider. So the windows are 1 by 0.6 meters. So 1 multiplied by 0.6 multiplied by 2 equals, that's 1.2 meters squared. And we have a door which is 1.75 multiplied by 0.8. I'm sorry, I'm going to have to use a calculator. Get our calculator up there. So we have 1.75 and we multiplied that by 0.8 and that equals 1.4. So we have 1.75 multiplied by 0.8 equals 1.4. Okay, so is that still there? No, it's gone. Just wanted to check that. 1.75 multiplied by 0.8 equals 0.4. Right. Okay. So we add those two together and we get 2.6. So 2.6. So 2.6. I like this wee calculator, so I'm going to use it again. So we have 34 minus 2.6 equals 31.4. So we have 31.4 meters squared is our total wall area for this building. Okay, so we can put in here 31.4. Excellent. That's our wall. Ground floors are going to be the same as up here, so that's the area of the ground floor. Windows, we've worked that out down here somewhere. There it is there. It's 1.2. And our door, we've worked that out as 1.4. You'll probably have a couple of doors. You'll probably have at least 2 doors or maybe more. We don't have roof lights and we don't have others. Now, if you are working out your wall area, please remember that 2.5 is the floor to ceiling height. So if you have another second story, okay, you are going to be multiplying this by 2. So this will be 5 meters. Okay, so this will be 5 by 3 by 2 because you've got 5 meters. It's not the overall height, it's floor to ceiling. So you add this one to the one above. So if, for instance, sometimes I've seen it before where you have a house that has 2 meters, 2.5 on the bottom and maybe 2.3 on the top. So you'll have to add 2.5 and 2.3 together. But whatever you have to do, remember, if it's a 2-story building, there's going to be another story, so you have to add it on to this ceiling height dimension. Okay, so there we go. Now, come to the U values. We'll do the roof first of all. Now, these U values, as you can see here, are in table 39. So down here at the bottom, you've got table 39. So what I've done is I've given you a list of typical U values. So if we go down to pitch roof, the U value for standard pitch roof is 0.15. So we'll stick 0.15 in there. Good. We'll skip wall for now. Ground floor. Down here, floors, use table 2.15. Right, okay. Floors are a wee bit complicated to work out because you have to take into consideration the perimeter of the floor and the depth of the floor and such things. So they're a wee bit complicated. What I would suggest is we will take an arbitrary figure. It doesn't matter. We'll just take a figure. So we'll take a figure there of, say, solid wall 2.3. So we'll use that 2.3 figure, which sounds as if it's pretty realistic. So 2.3 is what we'll use for our floor. Windows, there's a number of options. We've got double glazed, triple glazed, single glazed, blah blah blah. So I'll go for the standard double glazed 2.7. Sorry, that's my phone. 2.7. And then we will then look at our door, which is probably going to be the same. Some houses don't have the same door, but if you've got a new double glazed units, PVC double glazed units, the likelihood is your door is going to be the same as your window U value. Now, back to the wall U value. The wall U value is what we worked out before. So if we go down here to our previous calculation, we will see our existing U value for our wall, which is this layer, these layers here, is 1.73. So that's what we use. We use 1.73. And that will give us then the watts per Kelvin, which is which basically equates to our heat loss through the fabric of the building. So that is the heat loss that comes from inside the building here to outside the building here. Didn't draw that with my wee pen, but it's not so bad. So that's what we're talking about. There's heat inside the building, and that heat is dissipated out through the walls of the building, and the doors, and the roof, and the floor. So it goes up this way, and it goes down through the floor that way. It goes out through the windows, and it goes out through the door. There you go. So we have done all those. So we've told it the area, we've told it the U value of each of these elements, and we have got a total, which is this part here. If you click on that, it shows that it's the sum of H18, H and H2H24, H24. So that's that whole column is just added up in that column, in that space, and that cell is the column. Okay, that's grand. So we've got all that. That's really the main. That's the main item this is used for. So we will. What will we do? We'll just we'll blank that out. Click new. Yeah, new. Oh, it wants us to save that. Save as a room. Save that. Okay, so blank out. That doesn't distract us anymore. Well, we might as well make this. Oh no, that doesn't look good. Yeah, we'll keep it that size. Okay, so right now, specific heat loss due to ventilation. This is a measurement that again is given to you in table 40. This is the amount of heat loss that is lost because of the air being replaced in the building on a constant basis. So table 40, it gives you ideas of old buildings which has which would have that amount of heat loss. Family houses, specific heat loss. So this is watts per meter cube Kelvin. This is how much heat loss is being exchanged. Sometimes you'll find public buildings, for instance, will have more because there's a lot more people in it, as office buildings do. Single family homes 0.14. So let's program 0.14 in here, 0.14. And that gives us then heat loss due to ventilation. So we have 2.4 because if you notice it has multiplied H34, which is what we give it, multiplied that by H12. So H12 is the volume. So it's multiplied that by the volume. Makes sense. That's why we get that figure. Heat loss due to thermal bridging. This is a number it calculates itself because it uses 0.15 as a standard ratio. So it doesn't matter how big your building is, it will multiply it by 0.15. So you have 0.15 at the end here, and it's multiplied by H29. So H29 is the amount of heat loss. So it's a factor of this heat loss. It's 0.15. So it's 15%. 0.15 is equivalent to 15% of that figure, which is that. There. Yeah, there. Then you have heat loss total. So this is fabric, ventilation, thermal, and as you might have guessed already, it's just adding up these three figures. So we've got H29, H36, and H41. And that's the figure there. That's how much heat loss is being lost out through the building, kilowatt per Kelvin. Sorry, watt per Kelvin. So now the next thing is energy from space heating. Degree days. I'll explain degree days better in the class, but degree days is basically based on a figure of this part of the country, I think it's 15.5 degrees or 15 degrees. We'll keep it easy. It'll 15 degrees. So it's based on a figure of 15 degrees. If the air temperature outside drops below 15 degrees to 14 degrees for a full day, then that is considered 1 degree day. So it means that there is 1 degree of heat has to be generated to keep that building up to temperature. By the way, 15 degrees, it has been established again by research that 15 degrees outside will equate to 18 degrees inside, which is a comfortable temperature to keep a property. So 15 degrees outside will equate to 18 degrees inside the building because of internal gains, lighting, human heat coming off people, activities, all that kind of thing. So that's what they've worked it out. So if it's 15 degrees outside, it's a comfortable temperature inside. There should be no need for heat inside the building. But if it drops to 14 degrees outside, there will be 1 degree of heat required in the building, and therefore that will equate to 1 degree day. Table 21 shows us that. This is what the way it's worked out. But you don't have to worry so much about this. But this, like, you can see down here, this is the number of days in the month, down to 31. Obviously, some don't have 31 days. And then across the top, you have the months. So it's the months across here, goes all the way up to 12, and then it will give the below figure and the degree above figure, and that there is that's based on 15. You see here it's based on 15 degrees, 15.5 degrees, etc., etc. So this is for January. Sorry, this is not for the months. This is for different degrees. These columns. This is for January 2001. So this at 15 degrees, this is what we experienced here. We experienced nothing above but plenty below. So you can see here, if it gets to 15, it means that it was 0 degrees. Well, it didn't. It got to 1 degree down here. Okay, and then down at the top you get a total degree day for that month, which is 314 degree days for that 1 month. Hopefully that makes sense. Anyway, we don't have to worry so much about that. What we want to worry about is this wee table up at the top. So we are based here, say in Ireland. The more degree days that you have, the colder it's going to be. Because we're in the north, I would say we should use a figure of around about this one here. So 2,500 is what we will use. So we go in here, plug in, should I say, 2,500, and that will give us the energy to meet space heating demand for the year. So you see here it says kilowatt hours per year. So energy to meet space heating is this, equals to 0.024 by degree days by HL. So HL, if you see here, is H49 is the degree days, and H44 is the total heat loss. Okay, and they've multiplied that all by 0.024, and I can't remember what. Now I remember working out what 0.024 is. I can't remember at the minute what that stands for. I'll maybe get back to that. It's if you can work it out, because it says here watts, kilowatt here, watts here. They've added hours because we've put in degree days, so there's a time in there. Maybe that's what that is actually, because that would be days. This is hours. Yeah, that's probably what it is, you know. Okay, so anyway, we'll head on. Then we want to know energy from water. So we want to know how much heat we're inputting for water. Again, we have a table here, table 42. Go to table 42. What was our floor area? We'll check our floor area. Floor area here was 12. Okay, so we go to 42. Our floor area is very small, it's 12, so we will use this figure for hot water. 695. So plug on 695. and that gives us the energy for space and water heating. So energy for space and water heating is equal to space heating, which is here, 51, H51, and water heating, which is here, which is H53. So I'm looking at this formula bar up here. Okay. Did something just happen there that shouldn't happen? Back. Nope. That's alright. Just seen numbers change, and I thought, oh. Okay, so then we want to see what our energy rating, because this figure here doesn't really mean anything. This here is the total amount of energy that is being used by your building. So the building that you have surveyed, this tells you then the amount of kilowatt hours per year that that building is using. Now that's okay for your building, and if you had a building that looked exactly the same as your building, then happy days, you can compare the two. However, we don't have that, so what we need to do is we need to reduce it to a number that can be compared across buildings, and the way to do that is to divide it by the floor area, the FA here. So if you have a look here, click on that, what you'll notice is this number, which is H55, is divided by D11. Where's D11? D11 is there, the floor area. So now what we can say is we have a kilowatt per hour value kilowatt hour value per meter squared annum. So it means that it's per year. So it's kilowatt hour per meter squared per year. So it means that this here now can be compared with any other building. The last thing we want to do is we want to know what the heat load of the boiler is, because this here program was designed initially to establish the size of the boiler required for a property. So for that purpose we need to know the total hours of load per annum. Now this is basically, if you had your property and you had your boiler turned on and you were standing next to it with a stopwatch, you would discover that the boiler doesn't run for the full period that you've turned it on for. Or if you turned the boiler on all day, you would discover that it didn't run all day. It runs just for part of the day. So in table, oops, how do I get over there? There we go. Table 43, it gives you a guide for value of full load hours. So full load hours for Ireland is between 200 and 2000 and 2500. Again, we'll go for the bigger figure because it's colder where we are. So we'll go for that figure. I have to jump about a bit here. 2500. Okay. And that gives us the size of our boiler in kilowatts. It's very small. It's a 2.88 kilowatt boiler. But remember, the size of our wee shed, it was basically a wee shed because it's only 12 meters squared. It's a very, very small wee house. It's only 3 meters by 4 meters, so it's a very, very small wee house. Not very realistic. Okay, so that means we now have, this figure is the one that I want you to focus on, this one. So we have a kilowatt hour output per meter squared per year of that, okay? The last thing that you need to do now is you need to, so what you do is you print this off. So you print that off, and then what you do is you print a second one off, and the second one has our new U value, because remember we have calculated the heat load of the building for this wall construction. Now we want to do another heat load calculation with this wall construction, and this one has a different U value. This one has 0.3, 1 as a U value. So we will go back into our calculation. We will go all the way up to the top, and we will go into the U value for the wall, and we will put in there 0.31 and see what happens. So we come back down again. Immediately we see that the U value has dramatically changed to 344.3, roughly what, half of what we had originally. I didn't take a note of what it was, but it's roughly about half. Let's see if we do that. I think, yeah, it's 600. Do that. It's 300, not quite, but not far off it. So you could say that you are saving half your energy. In your project, what you would say is, we are using, say we are using £800 worth of fuel per year. If we make this modification, we will be using £400 worth of fuel per year, equaling a £400 saving per annum. To install the insulation in our building, it will cost us, say, I don't know, £2,000. Therefore, it will the savings will be recouped over a 5-year period. Isn't that right? Because what we've done is we have taken, I didn't close that, we have taken clear, yeah, so we have taken, say, £2,000 expenditure, and we sorry, that's the wrong way around here. We've taken £40, 400, sorry, £400, and we have divided that by 2,000, because that's how much it costs us to install this new insulation, and that gives us a figure of, no, I've done it wrong, haven't I? 2,000, yeah, divided by 400 equals 5. So it means that we have, over a 5-year period, we've paid for it. The payback period is 5 years, and after 5 years we are going to be saving £400 per year to go towards our holiday to Florida. Happy days. Okay, so that is that's the end of that tutorial. I hope you found it interesting, and I hope you are able to go back. If you have any questions, please email me, mark.mcguigan@swc.ac.uk, or talk to me in the class or in the tutorials. But that's 27 minutes, so hopefully that didn't bore you too much, and I'll speak to you soon. Bye.